To spend our second day looking at rotations. The last class was all a review, something that we saw from 2D kinematics. It was how to understand rotation in terms of angles that are being swept out as something is spinning around or moving in a circle trajectory. The angular velocity, the angular acceleration, how those all influence each other over a given amount of time, and keeping track of a centripetal acceleration. Anytime some sort of an object is moving in this circle, there's an acceleration built into it because that velocity vector is changing its direction. That's that centripetal acceleration, and it requires some sort of net force. So anything moving in a circle required that. Okay? We're going to continue that. So this chapter 12, it's a big unit. It's going to take up 4 different lectures, and we're going to start to look at a couple of new properties. Okay? So again, we've got, why are we understanding this? Okay? A big portion of physics and how this all started out for us was that we were trying to understand motion. Okay? And we had this really simplifying model where motion would be understood in this projectile piece particle model, where anything's mass and its shape all sort of condensed into just a single point particle containing all that mass. Well, if you have something in real life, it's not going to be just a single point, or especially if you're moving on to engineering and other types of science fields. And we have to understand shape and what that does to motion. Okay? So this is going to lead to our rigid body model, where it's not a point particle anymore. You have some sort of object, it has a mass, and it's extended out over space. Okay? But the shape does not change as it moves. Okay, we're not worried about warping or stretching or anything like that. Okay, so looking here, like this wheel, this will be a rigid body. It has some radius, it stays at that radius, and it stays as a perfect circle within our model. Okay? Now, the group of how things move, we're going to see that a full description of how something moves with a shape. It's a combination of 2 different types of motion. You have translational motion. That's the center of mass. How that object's center of mass moves is going to follow our particle model that we've done already. And then how everything else moves away from that center of mass is rotational motion, characterized by thetas and alphas and omegas inside of there. And it's this combination of them. Okay. So, I used the word center of mass already. I think it's something that everybody has a rough idea of. It's where everything sort of, where everything is centralized in if you're thinking about a mass moving. But physically and mathematically, what it means is that it's a point in some sort of an extended shape where it looks like all the forces are acting at that point, like a center of mass or a center of gravity, right? So if I'm looking at this gymnast, her body's stretched out over space. Now, every one of those molecules that makes her up has some sort of a mass, and each one of them is going to get pulled down by gravity, creating a force. Okay? And that force is going to try to rotate around this bar. Okay? But rather than looking at this person's individual molecules, we can treat her just as having all of her mass concentrated at this one location with this one weight vector, and it's going to create that rotation that goes around it. Okay. So there's a couple of web links. I have a nice video here that shows projectile motion. Okay, a combination of translational and rotational motion. So we'll watch it in real speed first.
Go.
Okay. So if I take it back, what you see are these 2 lights. Okay, the blue light is the center of mass, and the red light is just some point off of the center of mass. So this physicist throws this shape through the air, and what we want to do is see how it moves. Okay, and watching it in real time is kind of hard to see, but you can start to see the red just whirling around. It's following that rotational motion. And the blue light follows the projectile motion that we've seen before, okay, where you break the component, the position into its x and y components and apply gravity in the y direction, right? We'll watch it again. So it's a nice projectile following that quadratic. We can watch it in slow motion and see that red whirl around while the blue light follows easily predicted model. Okay. All right, so what we need to do is figure out how to calculate the center of mass or center of gravity, same thing for our class, okay? And to do that, you have to sort of do this weighted sum, right? Forgive the pun in there, where you're looking at where the mass is located at, okay? First, you need to set up a coordinate system, okay? Find an x and y axis, and then look at where the masses are, and then you work with the x direction, look at the x location of your different masses, add the product of those, and then divide by the total mass. And you do the same thing for the y. And what this does is sort of fills out where the mass is located. If you have a lot of mass over here, your center of mass is going to be close to where the large group of mass is. If you have it spread out all over the place, it's going to be somewhere in between. All right. So let's look at an example. Here we have an object. So you've got some sort of massless rods connecting these different objects. You got object 1, it's 1 kilogram. Object 2 with a 1 kilogram mass, and object 3 with a 2 kilogram mass, all located at this 1 meter away from it. Okay. So we've got this. What we're going to do is you have to pick your coordinate system. Okay, so I'm going to do it right here. There's my y-axis. And there's the x-axis in here. Okay. Now we've got these different objects. With the different masses inside of there. Okay, where you've got object 1, object 2, object 3. Okay, so our x position. All right, overall 3 objects in the way that it's presented in the book. You have, let me zoom back out a little bit. X center of gravity is equal to x1 m1 plus x2 m2 plus x3 m3 all over the total mass. Okay, so it's the x location for mass 1, the x location for mass 2, the x location for mass 3. All right, so let's figure those out. So the location, the x position for mass 1, mass 1's right here. It's located right at x equals 0. So I would go 1 kilogram times 0 meters plus, and then I look at particle 2. Particle 2 is right here. It's also located at x equals 0. So I go 1 kilogram at x equals 0 meters. And then I've got particle 3, 2 kilograms, but its x location is 1 meter off to the side. Now I need to divide by the total mass of the system, or mass 1, 1 kilogram, plus mass 2, 1 kilogram, plus mass 3, 2 kilograms. 1 kilogram plus 1 kilogram plus 2 kilograms. Plug all those in, and we get 0.5 meters. I'm sorry, yep. Okay. Half a meter over. Okay, so it's going to be somewhere over here, right? There's my center of gravity for the x position. Okay, so somewhere on that line. That's only one coordinate. We also need to find the y coordinate for the center of gravity. So we would do y center of gravity is equal to y1 m1 plus y2 m2 plus y3 m3 all over the total mass. Okay. And that's going to be, okay, y1 is 1 meter. Okay, particle 1 is 1 meter up in the y-axis. So we go 1 kilogram times 1 meter plus, and then particle 2 is located at y equals 0. So we get 0 plus 0. Particle 3 is also at y equals 0 meters. Okay. All over the total mass, which was at 4 kilograms, which gives me 0.25 meters. Okay. So that's the y location. Okay. So it's going to be about a quarter of the way up, and it's right here. Here's the center of mass. Or center of gravity for this class. Okay. So if I had this system, these weights, 2 kilograms, 1 kilogram, 1 kilogram, and I was able to, throw it or somehow get it through the air, everything's going to rotate around that center of gravity. Okay. All these different points. That one location is going to just follow the nice, projectile motion that we've seen, and the rest are going to rotate around it. Okay. Excellent. All right. So that's one concept that we have to do, and that was coming from discrete masses. Okay. We also have, continuous masses. If you're looking at, that gymnast, you can't just break her up into this gigantic sum. Or if you're looking at a disk that's rotating, okay, or if you're looking at just some sort of other extended shape, you need to treat it continuously. So those sums become integrals. Okay, our integrals are the way that you add up a whole, an infinitely large number of these infinitesimally small little pieces. Okay, and it follows the same way. What you do for your x center of mass, you look at 1 divided by the total mass, and then you integrate each little dm, okay, each little bitty mass, and where that mass is located at. Okay, this dm, it's a little tricky. You have to look at your system. If you're doing it in one dimension, and this is what we're going to stick with, right? You can look at the dm. What you want to do is get it in terms of something you can integrate, and you can integrate distances much easier. So you change the dm to where it's at linear mass density, this lambda. It represents the mass divided by the length. If it's a uniform object, total mass divided by total length, or if it's heavier on one side, it accounts for that. Okay. And then you get a nice dx that you can integrate against x. Okay. And then you do the same thing for the y direction. So we'll do an example in just a minute. Okay. Now here's a checking understanding one. So what you want to do, in just a second, pause it, read the question, and then try to answer it. Okay, so pause, unpause, and the answer is going to be A in this case. So your center of mass, or center of gravity, gets pulled, sort of follows the mass in this case, right? So this bar up at the top, it's going to start to pull the center of gravity a little bit towards the right. And this bar, extending downward, is going to sort of pull the overall mass down in that case, okay? You're not going to have a center of mass right here. B, it's too close to the left. D, it's too high up. So it's going to smear it out in between. And it's going to sort of average between these 2 points. And that's what's going to get you A. Okay? C, it extends too far. So let's do a couple of workbooks, problems 8 and 9 from this week. All right, so hoping that those looked well, we're going to look at how to calculate this with the integral. And I don't want to do the whole thing. What I want to do is focus on just this one bar off to the side. Okay, this piece right here. I want to try to find out where its center of gravity is. If you want to do the whole thing, what you would do is find this bar, and then you could find this bar, and then you treat those as point particles and average over their center of mass with that sum that we were working on. Okay. Oops. Sorry. All right, so let's start to look at that. Okay, so what I was saying is that I'm just going to do this piece. Try to find, and looking at the picture, you might think that the center of mass is going to be B, and that'd be a good guess because it's a uniform rod. There's nothing, we're not given any sort of extra information about it, that it's heavier down at the bottom or at the top or anything like that. So it should be around B in that case, and let's try to find that out. So here I've added in a couple of measurements. So the width of the bar is 1 meter, the length of the bar is 5 meters, and the whole mass of the bar is 5 kilograms. All right. So we'll do the center of gravity in the x direction first. The way that the book represents it, right, is this integral 1 over the total mass, and then you integrate x dm. Okay. Now, that total mass, we know that that's 5 kilograms. Okay. So we know that 5 kilograms, and then this x dm. Now, what we do with this dm is that we change it around a little bit, so the integral becomes 1 over m. And then we go from like x initial, how do I want to say this? X, we'll call it x0 to x1, x, and then that dm, I change it where I use the linear mass density times dx. Okay, and this linear mass density is going to be the total mass divided by the length in the x direction. Okay, of this object. Okay, so how wide is it? And that's 1 meter. Okay. Okay. All right. So looking at that, we've got it. We've got to plug this in. So that it's going to be a constant as well because the mass is 5 kilograms. The length in the x direction is 1 meter. So you get the whole integral 1 over m times lx, right? And then again, that lx is 1 meter. Okay. Now my integral goes from x0 to x1, or starting over here and then moving off to the side, and then x dx. And let me just be specific about my coordinates. There's my x-axis, and then I'll pick the y-axis right there. Okay. So I've sort of picked it funny so we can work with these bounds a little bit more carefully. So the origin's right there at the top. You don't have to put it right there. You could put it down here or over here or up there or right here at B if you wanted to. So this thing, if we start to treat it how it is, you would get 1 over mass times the mass over the length in the x direction. You get 1 over 5 kilograms times 5 kilograms over 1 meter. And then I integrate from 0 meters to 1 meter times x dx. Okay. I'll be a little bit more careful on my 5 kilograms. Okay. So I plug that in. I'm left with 1 over a meter times, and then when I integrate x, right, that gives me x squared over 2. And then I have to evaluate it at the two ends. 1 meter, from 0 meters up to 1 meter. So I would go 1 over 1 meter times 1 meter squared over 2 minus 0 meters squared. Okay. Once you plug in, I'll be a little bit more careful. So I go right here, 1 meter squared, that gives me 1 over 2. And I'm left with 0.5 meters. Okay. So it tells me that the center of mass of this highlighted object in red, it's going to be half a meter over. That's good, because just looking at it, it's a uniform object. That center of gravity should be contained right in the middle of it. Okay. You can go ahead and guess that the y center of gravity is going to be halfway in the y direction as well. But I want to do the integral and practice it. Okay. y center of gravity, 1 over the total mass times the integral of y dm. Okay. Now we change that, 1 over the total mass and the integral. I'm going to go, that becomes y, and my dm becomes lambda dy. Okay, I'm going to integrate from y0 to y1. Okay, so from my lowest point up to my highest point in the y-axis. And this lambda, it's the total mass divided by the length in y. Okay, so that would be 5 kilograms. And then how long is it stretched in the y direction? Okay, it's stretched 5 meters total in that case. So now it's 5 kilograms divided by 5 meters. Is equal to, okay, 1 over m times m over how far is it stretched in the y direction. Okay. And now thinking about my bounds now. What's my lowest point? My lowest point, my origin's up there, but I'm starting down at the bottom and I'm integrating up this block. So I start at minus 5 meters. And I integrate up to 0 meters. Okay. And then I would get y dy. Okay. All right, so we get 1 over 5 kilograms here times 5 kilograms over 5 meters, and then the integral of y squared, of y dy, that gives me y squared over 2. So I get 1 over ly times y squared over 2 from minus 5 meters up to 0 meters. Plug in everything, and that gives you negative 2.5 meters. Okay, and so that moves you from that origin down right there. And so our center of gravity, it's going to be right here. Just as we figured. The x center of gravity moves it halfway over to the right. The y center of gravity is halfway down the y-axis. Excellent. Okay. All right. So the center of gravity, it's an important point. Everything moves around the center of gravity when this object starts to move under gravity or in any other type of condition. Okay. Now, we have another important quantity that we have to keep track of, and that's going to be the moment of inertia. Okay? We're going to see in just a little bit how this plays out. And it's going to give us a recharacterization of Newton's second law. It's telling us how hard it is for an object to rotate. Okay? So whereas mass or inertia told you how hard it was to accelerate an object, this moment of inertia is going to tell us how hard it is to rotationally accelerate an object. We'll see that in a little bit. Okay? But it works very similar to the center of mass. Okay? Center of mass was this sum characterizing where the mass is located at. Okay? This is the same type of thing. Here we're going to sum over the mass, but it's the mass with respect to what it's rotating around, squared. How far away this mass is extended from an object, okay? From your center of rotation. Okay, so you could sum over mass times r squared, and this r is, again, how far away the mass is trying to accelerate. And then you integrate r squared versus dm. Same thing, if you have a continuous distribution of mass. And then we have another rule that there's this parallel axis theorem, where if you know the center of mass, the moment of inertia about a center of mass, then you can find it in an axis parallel to that just by adding on this total mass times how far away that axis is from your center of mass line. Okay. And again, I believe I apologize, I put my mass densities on the wrong slides. So here you should be looking at a 1D, 2D, 3D type thing. And the last one, the center of mass, should just be, you'll focus on the 1D. But this moment of inertia, you can have a couple of different combinations. You could look at a 1D object, maybe like a really thin bar, or you could be looking at a 2D object like a plate or a disc, or a 3D object, something with a little bit more size in all the different directions. Okay? But it's going to work the same way, where you look at your DM, you break it up into mass densities and the directions that you're integrating over. Okay. Now the book does this for quite a few different shaped objects, and you're free to use this, right? So if I give you a problem like this on an exam, I'll provide you with these tables of moments of inertia. You'll be able to use it with your notes and everything. I don't want you to have to derive these at any time. If I specifically ask you to derive it, you can do it, right? You do that integration. But if I don't, use the tables. They've been done. They're ready for you to use them. They're just tools to use now. Okay. So here we have a couple of examples. This is a thin rod, any cross section about its center. So you're talking about some sort of rod, and it's this black line right here is what it's rotating around. So it's spinning off in those different directions. Okay. And then notice here's a thin rod, but rather than going about its center, it's off to the side. Right? So in this case, you could actually solve for this using that parallel axis theorem. And you notice that the moment of inertias are different. Okay? The moment of inertia up here, it's a little bit smaller than this one. And that's because the mass is all closer to your axis in this case. And that this moment of inertia is seeing how hard it is to rotate the mass. So the further away the mass is, the harder it is to rotate. So a little bit more here. That's because it's got the mass extended further away from your axis. Okay? Then you got planes. Here you've got a solid sphere, a spherical shell, a hoop, and cylinders or discs or something like this. Okay? They're hiding back here. Right there, 1/2 mr squared. Okay. All right. So with that, you'll take that and do a couple of workbook problems. Look at 10 and 11. Right. So let's say, what's the moment of inertia of a disk rotating about an axis that runs through its center? Okay, and what if it's rotated off center? Okay. Now looking at this one, you could look at it and you could try to pull off the, draw a picture. What's it looking like? You've got a disk. Okay. And then there's some axis that runs through it. Okay. And this disk, it's rotating around it in that case. All right. All right. So one way to do it is you go to that spreadsheet. You say disk. This is a rod, so no, I can't use that. There's a rod, I can't use that for a disk. Plate, I can't use that for a disk. Blah, blah, blah. Right here. This top right one, it tells me it's a cylinder or a disk, and it runs off like 1/2 the mass times r squared. Notice it's got the same axis in there. Okay? So 1/2 mr squared, where r is how big that disk is. All right, great. Well, but let's try to do it. We'll spend a little bit of time with the calculation. I is equal to the integral of r squared times dm. Okay. Where what you want to do is think about this little bitty slab in here where you integrate out to that point, little r. So you've got this big disk, and you're going to look at a little ring right here. How big is it? And then a little bit, add that to a little bit bigger ring, and a little bit bigger ring, and a little bit bigger ring inside of here. Okay, so this becomes my integral. It's a 2D surface, so we go r squared, and then that dm, I'm going to change it to sigma dA in that case. Or if you want to cut to the chase, maybe you've been doing multivariate calculus, you say, well, it's cylindrical symmetry, so I want to use RDR. The circumference 2 pi r times the width dr. Okay. Let me see how to do that. Okay. So this, I'll look at dA in just a second, but that sigma, it's the area mass density, which is going to be the total mass divided by the area, or m divided by pi r squared, okay, where the total radius of this disk is big R. Okay. And this dA, think of it as it's the area of this little bitty ring that we're integrating. Okay, so it's going to be the length around it. Okay, that's my circumference, which is equal to 2 pi r. Okay, where that's r, and then times the width, how wide that little area is inside of there. Okay, and that is my dr. Okay, it's that little bitty strip around this integral that we're doing in here. All right, so I can plug that in. My integral, I go from 0 out to big R of my disk. Then I go r squared. Sigma is the mass over pi r squared times dA, which is, oops, let me be careful about this. I wrote the circumference. I shouldn't have put the dr right there. That's my dA. My dA is the circumference times the width, which is 2 pi r dr. We could pull out everything that's constant. Okay. Actually, our pi cancels, but we're going to get 2m over big R squared. So 2m, our pi's are out, and then we get r cubed dr. Which is equal to 2m over big R squared. And then when you integrate r cubed, what you get is 1 over 4 r to the 4th. And then evaluating it at the bounds, 0 to r, big R. Okay. So plug that in, 2m over r squared times, I go r to the 4th over 4 minus 0 to the 4th over 4, which gives me my r to the 4th cancels with that r squared, gives me an r squared. My 2 over 4 gives me 1/2, and I go 1/2 big M r squared. All right, so we got it. We got the result we were looking for. You use a table. That's a good way to do it. That's a clever way to do it, unless you're specifically asked to evaluate it. Yep. All right, so that's the moment of inertia about this axis that runs right down the middle of it. Now, what it's asking you for is what happens if you pick a different axis. And now you start spinning it. So you're not spinning it along that right in the center now. Here you got sort of a bulge out to the side, and it's just rotating around. In that case, your disk is now rotating like this. Okay. For that one, that's when we use the parallel axis theorem. Okay, and we have to know how far away we've moved that new axis over. Okay, so let me move this one down. Okay. For the new axis, we use the parallel axis theorem. We can use the parallel axis theorem because our new axis is parallel to it. Okay, we just calculated the moment of inertia for this red axis right down the center of the disk. Here we're going to look at it rotating around a different axis just off to the side. That's a distance little d away from there. Okay, so our moment of inertia in that case is equal to the moment of inertia about the center of mass plus the total mass times d squared, or 1/2 mr squared plus md squared. You can clean it up just a little bit. R squared over 2 plus d squared. same thing. So you plug it in. It becomes a little bit harder to rotate now, right? You've got this, your mass is now moving around something that's a little bit further out. It becomes, that moment of inertia goes up with it. Okay. Great. All right, so here we got a checking understanding. We're going to sort of swap gears a little bit and look at something new, but it's something that I think we all have intuition built up on. Okay, so here, pause, unpause. So over here you got the door. Which one how do you want to pull on it or push on it? It's going to be F1, okay? When you're pushing perpendicular to the door and as far out as possible, it's easier to open up, right? If you're real close to the hinge, much harder to open in that case. If you're just shoving the door into the hinge, it's not going to rotate. And then if you pull off at an angle, it will open it, but it's not going to be an efficient way to open it. Okay? And this is going to start to underlie our understanding of torque. Okay? Torque is going to play the same role as a force, but in terms of a rotation. So here, we're looking at some sort of an object and we're trying to get it to rotate. So for example, we're trying to apply this wrench on a bolt and get it to spin. Okay. If you push in or if you pull out on the wrench, nothing. That's not going to do any sort of any type of rotation for you. If you do it at an angle, there is going to be some rotation, but it's not going to be efficient. What you want to do is apply your forces perpendicularly, depending on if you're wanting to tighten it or loosen the bolt. Okay. So, and in order to understand that, we need positives and negatives. We saw this before with rotations. That's what the last lecture was about. Counterclockwise rotation is positive. Clockwise rotation is negative. So we're going to have to take that and stick with it. So this force vector right here, it's trying to rotate about this axis. So it's trying to spin this whole system in this direction. Okay. In that case, that's counterclockwise, right? So the way the mouse is moving, that's counterclockwise. It's going to be maximum positive torque. You're getting the maximum attempt at rotation, and that's what we define as a positive direction. Here, you're going to get maximum attempt at rotation, but it's going to try to rotate it clockwise, okay, the way my mouse is moving. Okay? So it's coming down, and that's what we call negative. Okay? Now, we need to be able to calculate it. And what tries to cause the rotation, what creates the torque, is only the component of the force that's perpendicular to the line connecting the pivot point to where the force is being applied at. So you have the distance away from your point of rotation out to where the force is applied. And only this component of the force, the one that's perpendicular, F perpendicular, contributes to the torque in that case. Okay. So we'll see later on, we can treat this with a cross product. But the torque, it's going to be dependent on how far away the force is being applied, right? So a large distance away, you're increasing the torque. And then a large perpendicular component, you're increasing the torque. Okay? But that perpendicular piece, pulling it off, it's F, the magnitude of the whole force vector, times, it's over here, it's opposite that. So our angle phi, so sine phi in that case. Okay. Let's do an example. Here we have a 20 centimeter long wrench. We're using it to turn a nut. The wrench handle is tilted 30 degrees above the horizontal, so it's up here. Lewis pulls straight down on the end, so that's this dark red line pulling straight down. With 100 newtons of force, how much torque is Lewis exerting on the nut? All right. We'll do that, and we'll start to look at it. So it's already done a lot of the geometry in here for us. Here's our axis of rotation, right? So how far away is it from the point where the force is being applied? That's at 20 centimeters. Okay. Then we need to find out our angle from that line to our force. Okay, that's right here. That's what's done already. 120 degrees and negative in that direction. Okay. So I would say torque is equal to R F perpendicular, or R, this is our magnitude of the torque, F sine phi. So I plug it in. our radius, or distance away from the pivot point to the force being applied, is 0.20 meters. The force, the magnitude, is 100 newtons of force. And then you would go sine of 120 degrees. Just a second. All right, so I go 0.2 times 100 times sine. And in Mathematica, I reads things in terms of radians, so I have to do 120. I have to convert that to radians, so I do times pi divided by 180. And that gives me 17.3 Newton meters, but we're just going to make that approximately 17 Newton meters, right? It's the same thing as a joule, okay? Same thing as a joule, but just out of convention, whenever we're talking about energy, we'll call that joules. Whenever we're talking about torques, we're going to call that Newton meters, or maybe you've seen it as foot pounds and things like that, okay? Ideally, if you put joules, you are still correct, but we just like to say Newton meters instead, to say we're talking about a torque instead of an energy. So it's 17 Newton meters inside of here, but we also need to be careful. Okay, which way is it trying to rotate? So I look here, and the way the force is going down and the way that we're oriented, it's trying to rotate it clockwise in that case. Okay, the force is trying to cause clockwise rotation. Okay. So this would be a negative 17 Newton meter torque. Clockwise. Okay. And once we come up with our complete vector description of it, we'll say negative 17 meters. But we're just introducing it now. Okay. Excellent. So we'll call it on that. In the next class, we're going to start to calculate torques and rotations and how those all work out together. Excellent. Thanks.